Here we have a circle representing the Earth. This says mass m sub Earth. Now the mass and the Earth, I don't know if they're going to be legible, but that's just the mass. We've got mass m sub Earth. And we got a mass little m orbiting the Earth in a circular orbit at 7,000 kilometers. Okay, so the radius of this circle is 7,000 kilometers. The orbiting object, the orbiting mass, is 7,000 kilometers from the center of the Earth. Now, again, we know that the force exerted on the Earth is some proportionality constant multiplied by the product of the masses divided by the square of their separation. The two masses in this case being the Earth, mass of the Earth, and the mass m, little m, which we're going to take as the mass of the satellite. Separation of the centers of mass is r squared. G is our proportionality constant, which, according to our early data, was around 7 times 10 to the negative 11th Newton meter squared per kilogram squared, and which has accurate value 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. That might be a little hard to read down at the bottom of the screen, but I think it should be. It's not written very well, but it should be kind of legible. Anyhow, we're going to be seeing that quite a bit, but that's the value of G. Okay. And we're not going to use the value of G in calculating this, just letting you know there is a value of G that has been measured in the lab to a number of significant figures. Okay. Now, this is the gravitational force on the mass. Now, orbiting out here, there are no other large objects close by. The moon's out there, but it's pretty far away. It doesn't exert a whole lot of force on this mass. The sun exerts a force, but not a whole lot. So we can ignore all that and just say that the net force in this object, and of course it's at 7,000 kilometers from the center. There's not any atmosphere, any appreciable atmosphere out there, a few stray particles. There's nothing to cause this thing to have any significant force of something like air resistance, okay, atmospheric resistance. So the net force, the only thing to exert the force on is the Earth, so the net force would be the gravitational force. Now, assuming then that the net force is equal to the gravitational force, the acceleration of the mass little m is what? Well, net force is this, mass is this matches this, so if we divide the net force, gravitational force being the net force again, by little m, we're left with big G, mass of the Earth, divided by r squared, and that's what we say here. Okay, the acceleration is F net over m equals ... equals G m Earth over r squared, and the ... is where we express F net as G big M little m over r squared. Okay, dividing out, we get this. So the other thing is now, if this mass is moving in a circle, then it has a centripetal acceleration, v squared over r. So it's got to have a centripetal acceleration to stay in the circle. That acceleration is v squared over r. So the centripetal acceleration, of course, is your gravitational acceleration. The only force acting on this thing is the gravitational force. If it's going to stay in a circle, it's going to have a constant centripetal acceleration toward the center. And that centripetal acceleration is a result of the gravitational force on this mass. So, okay, so the centripetal acceleration is equal then to the gravitational acceleration. Gravitational acceleration is this. So we set v squared over r equal to big G, mass of the Earth, divided by r squared, and solve for v. So this equation implies that v is the square root of G m over r. Now, I don't bother with the plus or minus, even though we're solving for a v squared. We're solving a v squared equals for v, because we're just talking about how fast this object is moving, not a vector quantity in this case. So that's the expression for the velocity of a satellite in circular orbit. Okay? Now, if we want to actually orbit a satellite in circular orbit, we need something a little better than the information we used in solving here and here. we need this accurate measurement of G, and having that accurate measurement, we can accurately calculate the velocity we need at distance r. Now I'm going to modify my previous comment just a little bit. We don't really need the G measured in the lab to do this, because if we take any mass on the surface of the Earth and know the radius of the Earth, the distance of this mass from the center, and measure the force of gravity on that mass, like just put it on a scale or an accurate spring balance or something we can measure with good accuracy, then we would know G times M Earth. Because we know this, this, and this, we could at least find the product of G times the mass of the Earth. Okay? So we really don't need this value in order to calculate this. If we knew just this information, we'd be able to calculate big G times big M, and of course, knowing r, we can then calculate the velocity we would need for a circular orbit. Okay? Now, if we want to know the mass of the Earth, then, well, we can solve this with just things that we can measure right here in the lab to get the product G times mass of the Earth. And we can measure G in the lab. We probably could measure it to 3 significant figures with equipment that we do have in this lab. We can't use it because it's windy in here, but it's very sensitive equipment, but that's an experiment that we would be able to do, and I would love to do with a good group as the one that we have right now. Once you've measured G and determined big G mass of the Earth, you can then, of course, divide that by big G and get the mass of the Earth, and that's how the mass of the Earth is determined. So take that for what it's worth.